A large circular disk of mass m and radius r is initially stationary on a horizontal icy surface. The person of mass m over 2 stands on the edge of the disk, holding a large stone of mass m over 20. The person throws the stone horizontally at initial speed VO in the radial direction, that's straight outward from the disk, as shown in this figure. So for part A, we want to derive an expression for the linear speed of the disk person system immediately after the stone is thrown. So, since the stone is being thrown straight outward, it's not going to cause this disk to rotate. And this is considered to be an explosion, even though there's no explosion that took place. When we talked about momentum conservation, we talked about collisions and explosions. A collision is when two or more items come together, and they may stick together, they may just collide and go apart again. But an explosion is when two items or multiple items start together as one piece and then separate. So just by throwing this object, it is considered to be an explosion where two items come apart. The first item being the combination of the disc plus the person, the second item being the stone. So because everything is translating and not rotating, we're going to set up part A as a conservation of linear momentum. So we can do that by saying P initial equals P final. And initially, the person is just standing on the disc, not moving, holding the stone. The stone's also not moving. So initially, there is zero momentum in the whole entire system. After the stone is thrown, the stone has a positive momentum because it's moving in the positive direction toward the right, which means the disc with the person on it is rebounding to the left in the negative direction. So the combination of the positive and the negative will balance out to give a final momentum that is also equal to 0 since momentum is conserved. So we can just write that by saying the final momentum is m over 20, the mass of the stone, times its velocity, VO, minus, now we need to get the entire mass of the disk person system, which is m plus m over 2, times its final velocity, Vf, and then all you need to do is just take this whole equation, simplify it, rearrange it, solve it for Vf, and you've got your answer. Alright, so now the person is going to stand on basically the same disk, same mass, same radius, but this time it has a fixed pole going right through the center of the disk. So it's fixed in place there, so it cannot translate, all it can do is rotate. So this time the person is going to throw the rock in the tangential direction, which will cause the disk to rotate instead of translating. Because it's fixed in place, it's unable to translate, all it can do is rotate. So we're going to set this one up using conservation of angular momentum. L initial is equal to L final. Now initially, nothing is moving. The person's just standing there holding the rock, not doing anything, so the initial angular momentum is 0 for the same reason that the initial linear momentum was 0. But the angular momentum after the collision consists of multiple objects, some moving clockwise, some moving counterclockwise. If you think about the motion of the rock, even though that is linear motion, it is going in that direction relative to that center point where everything's fixed around. This is in the counterclockwise direction, because if you imagine if this rock were to curve, it would go around like this, whereas the platform with the person on it after the rock is thrown is going to be rotating in the clockwise direction. So because the stone is moving counterclockwise, we're going to go and call that one the positive direction, and then we're going to call the platform person system, the disk person system, the negative direction. Now remember, there were two different ways to write the angular momentum. For a rotating object, we can write L is equal to I times omega. That's what we're going to use for the platform with the person on it. But for an object moving with linear motion, we have to actually write the linear momentum, mv, times the distance the object was from the center, which is the r. That's how it was written in AP Physics 1. For those of you in AP Physics C, we just wrote this as the way it's on the formula sheet is the cross product the vector cross product of r cross p, which then will end up simplifying to m times v times r. So same thing either way. So the rock, or the stone, has a mass m over 20. It has a velocity, VO, and the distance from the center point when that rock was first thrown is the capital R. And that whole thing is positive because we said that's moving in the counterclockwise direction. And then we're going to subtract the stuff moving in the clockwise direction, the disk person system, which has a total rotational inertia I and an angular speed of omega. The angular speed is what we're ultimately looking for, but in order to do that, we first have to come up with some expression for the rotational inertia of the disk with the person on it as it's spinning. So that I will equal to, there's going to be a disk component, plus there's going to be a person component. Now for the disk, it's just a really big flat cylinder, and if you look that up in a table, you'll see it is 1/2 mr squared. The mass of the disk is m, the radius of the disk is r, so 1/2 mr squared, plus, and then the person is just an isolated object on the disk that is revolving around the center point, and every time you have an isolated object that's just revolving around a point, the inertia is just always just mr squared. So for the person, it's mass times r squared. The mass of the person was m over 2, and that person is a distance, capital R, from the center, so it's m over 2 times r squared. So that's our total inertia of the system. It's 1/2 mr squared plus basically 1/2 mr squared again. When you add those together, that just gives you m r squared, and that's what you can plug in place of the I. Then you'll see that several things cancel out. The m and the r's will both cancel out. You can bring this whole term, the I omega, to the other side and just solve it for the omega. And then finally in part C, the person is throwing the rock the same way, tangential to the circle with speed VO, only this time it is not fixed in place. So because it's not fixed in place, that means it will still have rotational motion because the angular momentum is conserved, but because it's not fixed in place, it will also have the linear momentum conserved. So you can say for this one, in the brief discussion of it, that because there's no external forces on the system, the linear momentum is conserved, so the disk will translate in the downward direction, and because there's no external torques on the system, the angular momentum is conserved, so the disk will rotate in the clockwise direction while it is translating in the downward direction.